Bismillahirrahmanirrahim. Good evening, everybody. Terahertz waves are electromagnetic radiation with a frequency somewhere between microwaves and infrared lights. Also known as T-rays, they are produced by almost anything that registers a temperature, including our own bodies and the inanimate objects around us. Terahertz waves are pervasive in our daily lives, and if harnessed, their concentrated power could potentially serve as an alternate energy source. However, to date, there has been no practical way to capture and convert them into any usable form. Now, physicists at MIT have come up with a blueprint for a device they believe will be able to convert terahertz waves into a direct current, a form of electricity that powers many household electronics. Their design takes advantage of the quantum mechanical or atomic behavior of the carbon material graphene. They found that by combining graphene with another material, in this case boron nitride, the electron in graphene shall skew their motion toward a common direction. Any incoming terahertz waves should shuttle graphene electrons like so many tiny and traffic controllers to flow through the material in a single direction as a direct current. The researchers have published their results today in the journal Scientist Advance and are working with experimentalists to turn their design into a physical device. Over the last decade, scientists have looked for ways to harvest and convert ambient energy into usable electrical energy. They have done so mainly through rectifiers, devices that are designed to convert electromagnetic waves from their oscillating alternating current to direct current. Most rectifiers are designed to convert low-frequency waves such as radio waves, using an electrical circuit with diodes to generate an electric field that can steer radio waves through the device as a DC current. This rectifier only work up to a certain frequency and have not been able to accommodate the terahertz range. A few experimental technologies that have been able to convert terahertz waves into DC current do so only at ultra-cold temperatures, setups that would be difficult to implement in practical application. Instead of turning electromagnetic waves into a DC current by applying an external electric field in a device, Isobe wondered whether, at a quantum mechanical level, a material's own electrons could be included to flow in one direction, in order to steer incoming terahertz waves into a DC currents. Such a material would have to be very clean or free of impurities in order for the electron in the material to flow through without scattering of irregularities in the material. Graphene, he found, was the ideal starting material. To direct graphene's electron to flow in one direction, he would have to break the material's inherent symmetry, or what physicists call inversions. Normally, graphene's electrons feel an equal force between them, meaning that any incoming energy will scatter the electron in all directions. Symmetrically, isoB looked for was to break Grappen's inversion and induce an asymmetric flow of electrons in response to incoming energy. Looking through the literature, he found that others had experimented with graphene by placing in atop a layer of boron nitride, a similar honeycomb lattice made of two types of atom, boron and nitrogens. They found that in this arrangement, the force between graphen's electrons were knocked out of balance. Electrons closer to boron felt a certain force, while electrons closer to nitrogen experienced a different pull. The overall effect was what physicists call skew scattering, in which clouds of electrons skew their motion in one direction.